Hello everyone, my name is Angelo and today I would like to show you our demo application, which is a data marketplace where users can upload a piece of data, set a description, a title, and a price, how much it costs for other people to download this file, and then other people can go in, take a look at the files that are available for downloading, and then if they would like to download a file, they can pay the requested amount and download the file. And so let's go right ahead and log in here with Scatter. And we've got our Bob and Alice accounts, and we're going to start with Alice. She's going to share a file with us, so there are no files yet here. So let's change that and upload a file. And I've prepared a secret message here that Alice is going to upload here. It's just a small text file with a secret message in here. So we're going to drag that in here. Then here we can set a file name, so secret.txt. Then here we can set a description if we want to let other people know what this file contains. So this is top secret. We can set a price, how much this file costs to download, and then we can upload. And now Scatter wants us to sign a transaction, and this is just a message to our demo app smart contract with all the data that we entered. And now this is the IPFS URL of the encrypted file. So in this example, we are using IPFS to store the encrypted version of the file, some internal UUID, and then this is the actual store method that is sent to the previous contract, which is from the previous protocol, where we have all the pieces for the different nodes here. So let's not yet submit this. I'd like to show you this first. So what's happening in the background is when I hit this upload button, what's going to happen is we're going to generate a secret key in the browser, in the client, and then we are going to use Shamir secret splitting to split this secret key into 5 pieces, because we have 5 nodes running locally on our machine here in this test node setup. And when I submit this transaction, each node gets a share of this key. And what's interesting about this is that no single node has the full decryption key. So if this node, for instance, is bad, or gets hacked, they cannot decrypt the data. So that's really important. So let's do this. So I'm going to click upload. There's a secret key being generated. The file is being encrypted, uploaded onto IPFS. And then we're going to sign this transaction here using Scatter. And there we go. We have successfully uploaded a file. This shows you the URL where the encrypted version of this file is stored in IPFS. And we can also take a look at this encrypted file. And you can see it's all garbage because this file is encrypted. So that worked. Great. So let's go back to the files. We can now see that we have successfully uploaded a file. top secret by Alice. The price is 1 EOS. And now we're gonna log out and log back in as Bob. And Bob is going to purchase this file. So Bob now sees, okay, the same file. And I can now, as Bob, go in and purchase this file. All right. So buying weak access to file secret.txt. It's a token transfer of 1 EOS and some more stuff. So we're gonna sign this transaction. Aha, okay, so this seems to have worked, which means we can now download the file. Okay, there we go. And this is a secret message. So we've successfully paid the requested price that Alice requested, and we've been able to download this file. And of course, this doesn't work just with text files. It works with images, movies, secret documents, disk images. It works really with files of any size. And what's also very interesting to note here in this data marketplace example is that the purchase and the granting of permissions to the user Bob happens in a transaction atomically. So there is no nothing Alice needs to do in order to provide the file to Bob. And I can, since I have now purchased the file, I can even re-download it. So I can download it again, and there it is again. Here we go. So Bob has access to the file now, and Bob can download it as often as he wants. All right, so let's see. Bob now paid 1 EOS to Alice. So let's see. Let's log back in as Alice. And we can now see up here, proceeds 1 EOS. This means that this 1 EOS was transferred to Alice. So she made 1 EOS by selling this data to Bob. So I hope you like what you see. If you would like to know a little bit more about what's happening in the background, I can show you that now. So I have some nodes here running, 1, 2, 3, 4, 5, just locally here on my local machine. And of course, this is a test setup. This is just for testing. So normally you would only have 1 node per machine and 1 node per block producer. And this would be running somewhere in a data center. But since this is just for demo purposes, just still in development, we have all these now running on 1 machine. And then here, I have a Node.js local testnet running with MongoDB plugin that this will need. And then here we have a communication broker where the browser here connects to. And another thing to note is this browser application, so this application that's running in the browser is a React application. It's running entirely in the browser. It has no server-side components. The only thing it does is it only interacts with the EOS blockchain through one of the API endpoints. So this is a completely decentralized application. All right, and so if I could say cleos get info. So this is my local testnet, and I can also say clears get table PrivEOS rules. This is the name of a smart contract nodes, and this shows the nodes that have registered with our smart contract. So we have test node 1, test node 2, test node 3, 4, and 5 running all on localhost on different ports. So these would be those here. And when I upload a file, what's going to happen is that, as I said, the secret key, there's a random secret key being generated inside the browser. Where you're going to use Shamir secret splitting to split that up into 5 pieces, and each node gets one of those pieces. And right now it's configured so that in order to reassemble the original secret key, we're going to need three of the 5, 3 pieces of those 5. So that means even if like 2 of these nodes are not available, not running, we will still be able to reassemble the original key. And we can, in fact, we can actually test this. So from these 5 nodes that are running, I'm going to kill 2 of those. So these 2, node 4 and 5, are now shut down. So we have only like 3 nodes left running, which means in theory we should still be able to download our file. So let's log back in as Bob. Here we go. Now let's see if we can still download the file. Okay, it now requests a new access grant transaction with a new public key here, because we have restarted the browser. And there we go, it's still working. So now let's go ahead and kill another one of these nodes. So let's close this one as well. So we now have only 2 nodes left running, which means now if we try this again, it should not work. So let's see if this in fact will not work. Click on the download button. Okay, we get another transaction here, and yeah, there's no error message, but it's not working. You see, no download. And now we can go ahead and start one of these nodes again, or maybe let's start a different one this time, it doesn't matter. Okay, let's try this again. And look here, now it's working again. So we've been able to verify that in fact we have a system that is somewhat redundant against failure of single nodes. And of course, this is just a test setup with just 5 nodes. In reality, we would like, of course, a lot more nodes running. So we are aiming to have around 30 nodes in the beginning that will be run hopefully by EOS block producers. So we have a very high standard of decentralization if we have 30 nodes, and then for instance we can configure a threshold of 20 from those 30. That means even if from those 30 nodes, even if 10 of those nodes are unavailable, we will still be able to reconstruct the secret. So the service will still be running, even if a third of those nodes will be gone. And on the other side, no single node operator would be able to decrypt the file. So you need 20 pieces. We need 20 nodes to cooperate or to collude in order to illicitly decrypt the file. And since those nodes are run by EOS block producers, this is highly unlikely that 20 of those nodes would collude. So this gives the system also quite nice security properties. And this is really an improvement over traditional classical centralized key management services, where there is just one party in the middle that has access to all the keys. In this example, there is no single party that has access to the data. It's in the network. Yeah. So I hope you like what you've seen, and we are gonna hopefully release a new video soon, and we'll keep you updated about our progress. If you would like to know more, check out our website. So you can go to PrivEOS.io, which redirects to SLANT/PrivEOS. Here you can also download our white paper. And then also, if you would like, if you have questions or if you want to stay updated on our progress, there's a Telegram channel that I would recommend you to join. And of course, if you like this video, give it a thumbs up. Hope to see you soon.